Hello friends, welcome back to our channel Crash Course for the Engineers. In the previous session related to laminar flow, we have seen, we have covered the derivation for laminar flow for flow bit flow through a tube or pipe, and secondly we have covered laminar flow between two parallel plates when both are fixed. Now in this session we'll go through the derivation for laminar flow between two parallel plates. One is fixed and other is moving. And this is also called as a Couette flow. Now, this is the diagram. Uh, the link for the some of the theory related to the laminar flow between two parallel plates which are fixed uh, is already shared in the description of this video. So please go through it. Now I'll just go to the next step, important step. So here is the diagram. Now look over here. You can see black color plate is fixed plate and red color plate is a moving plate. The distance between the two plates is small t, and other things are same. So uh, we will start with the derivation part. Now friends, the relation for uh, u was u is equal to 1 upon mu into delta p by delta x into y square by 2 plus c1y plus c2. So this was the relation for the velocity profile. Now, for this case, we'll apply the boundary condition. So applying boundary conditions. So B dot C refers to boundary conditions. Now at y is equal to 0, so at the fixed plate surface, the velocity that is u will be equal to 0. Hence, if we put this value, so 0 is equal to 1 upon mu into uh, delta p by delta x into the value of y is 0, so 0 plus C1 into 0 plus C2. Hence, it means that C2 is equal to 0. So, we found a value for constant 1. Let us go for the next boundary condition. So, at y is equal to small t, u will be equal to the velocity of the moving plate, that is capital small v. So we get v is equal to 1 upon mu in bracket delta p by delta x, and the value of y is t, so t square by 2 plus c1t plus g. Okay, so let us rearrange the terms to get the value of C1. So C1 into T is equal to V minus 1 upon mu into delta P by delta X into T square by 2. So C1, so I can say C1 is equal to V by T minus, if I divide by t to this bracket, so and the t square 1t will get cancel out, so 1 upon mu into delta p by delta x into t by 2. So now we have got the uh, values for both the constants. So if we put these values in the equation for the velocity, so we can get u is equal to 1 upon mu into delta p by delta x into y square by 2 plus y into the value of C1. So that is C1 is V1 V upon T minus 1 upon mu into delta P by delta X into T by 2. Let us multiply by this value y into the bracket. So 1 upon mu into delta P by delta X into y square by 2 plus so Vy upon T minus 1 upon mu delta P by delta X into Ty divided by 2. So now you can see here something is common. So Vy by T. Now let us see what things we can take out the common. 1 upon mu delta P by delta X is common. So 1 upon mu into delta P by delta X I have taken common. So so I should have this value in bracket Ty minus y square, and this 2 is remaining. I should multiply it here. So this is the relation for u. By this relation, I can get the value of u at any location between the two plates if I know the value of y and if I know the value of t. So now suppose this is equation number 2. Now if we look at this relation, this value of u depends on delta p by delta x, also on the value of y. Now we know that this delta p by delta x is the pressure gradient. Now this pressure gradient may be positive or negative, or it may be zero. So if this delta p by delta x is equal to 0, if there is no change in the pressure, what will happen? This whole term, this whole term will become 0. So I'll get u is equal to v by v y by t. So this is the linear equation or relation. Okay, so the velocity distribution is linear between the two plates. Now let us find out the relation for the shear stress. Now friends, for this case, we can find out the values of u between these two plates at various locations, putting this value of y is equal to 0, y is equal to t by 2, and y is equal to t. Okay, so now, friends, let us go to the next part. to find out the shear stress. So we know that tau is equal to mu into du by dy. So let us put the value of du, sorry, let us put the value of u. So u is equal to v into y by t minus 1 upon 2 mu into gamma p by gamma x in bracket ty minus y square. Let us differentiate the relation with respect to y. So mu, the derivative, and multiply it by mu. So mu into derivative of vy by t, that will be into v by t, correct? Minus, if I multiply by mu, so this mu will get cancelled out. So I'll get 1 upon 2 and into gamma p by gamma x, and the derivative will be equal to t minus 2y. So tau is equal to mu v by t, and now is equal to gamma p by gamma x in bracket t by 2 into minus 1. So this is the relation for the shear stress. Now, if I want to find out the value of shear stress, so tau at y is equal to 0. So that is tau 0, 1, suppose, will be equal to, if I put the value of y is equal to 0, so I'll get mu into v by t minus gamma p by gamma x into t by 2. Tau at y is equal to t. So tau 0, 2. So mu into v by t minus, now if y is equal to t, so that will be equal to gamma p by gamma x into minus of t by 2. That is tau 0, 2 is equal to mu v by t plus gamma p by gamma x into t by 2. Now, if I want to find out tau at y is equal to t by 2, that is at equidistance from the both the plates. So tau at equidistance will be equal to, putting this value in the relation, what we are getting, mu v by t minus t by 2 minus t by 2, that is equal to 0. So at the end we are getting mu v by t. Now friends, if I want to find out the shear stress, where the shear stress is 0, so location, that is y is equal to what, right? So putting this value in the above relation, I am getting 0 is equal to mu v by t, sorry, minus delta p by delta x into t by 2 minus y. Now solve rearranging this equation for the value of y. So minus mu v by t is equal to minus delta p by delta x into t by 2 minus y. So t by 2 minus y is equal to, this minus will get cancelled out, so equal to mu v by t into 1 upon delta p by delta x. That is minus y is equal to mu v by t into 1 upon delta p by delta x minus t by 2, or y is equal to t by 2 minus mu v by t into 1 upon delta p by delta x. So see once again, friends, the tau value is equal to 0. So mu v by t minus delta p by delta x into t by 2 minus y. So taking this mu v by t to the left hand side, I'll get mu v by t into delta minus delta p by delta x into t by 2 minus y. So this is the relation for y. So at this value, the tau will be equal to 0. Now let us plot this on our diagram. So if this is the 0 line for the tau, so this will be equal to tau 0, 1, and this will be equal to tau 0, 2, and this will be equal to the value of y, where tau is equal to 0. So by this way I can draw the linear distribution for the shear stress. Now friends, this is quite difficult to solve derivation. If you have any query, please put it in the chat box. If you want any clarification regarding the contents which I have covered, you can feel free to chat put in the chat box. Thank you for watching the video.